Hello, dear students. I welcome you again. And today we'll continue with Mohr circle. We'll start Mohr circle today, and we'll also finish up what we have been studying so far. That is the basics of stress transformation equations, right? So let me just go to the slide. We've already seen the equations for stress transformation. Uh, the equations are as follows: the normal stress on any rotated element is given as sigma n, or we have also called it as sigma x dash, and it is equal to what? Sigma x plus sigma y by 2 plus sigma x minus sigma y over 2 into cosine of 2 theta plus tau x y into sine of 2 theta. And similarly, the modified equation for shear stress is what? Minus negative of sigma x minus sigma y over 2 into sine of 2 theta plus tau x y into cos of 2 theta. And this sigma x and sigma y are the stresses in the original conditions, and theta is what? The angle of rotation. And again, sigma x uh, sigma x is positive, sigma y is positive when they are tensile, and compressive when they are negative, and angle theta is positive when it is in the anti-clockwise direction, and it is considered to be negative when it is in the clockwise direction. And again, I would like to reiterate that these equations are valid only for the sign conventions which we have adopted, right? If you use a different sign conventions, these equations will change. These equations will not work in some different sign conventions, right? So in that case, you'll have to use different equations. But if you use different equations, you'll get the same result. Okay. Next, we have also seen in the class what is the maximum value of uh, the normal stresses and the shear stresses with respect to the angle of rotation theta. Like we have seen in case of uniaxial stresses that when we take non-transverse cut, the value of normal stress and shear stress is related to the angle theta, right? So when you change the angle theta, the value of normal stress and the shear stress changes. Similarly, in case of biaxial stress also, the value of the normal stress and the shear stress is related to angle theta. And as the theta will change, the value of the normal stress and the shear stress will change. So there will be some particular value of angle theta for which the normal stress will be maximum, and similarly there will be some value of theta for which shear stress will be maximum, right? So in order to find out what is the maximum normal stress, what we do is we differentiate this element, and one thing which you have to remember is that the stress is changing with respect to what? Theta. So we'll differentiate this equation with respect to theta and equate it equal to 0, right? And we'll find out what is the maximum normal stress. So the maximum normal stress and the minimum normal stress comes out to be like this: sigma 1 2. Sigma 1 is called as sigma 1 over here is uh, is called as the maximum normal stress, right? Or it is also called as the principal stress. And I'll tell you why it is called as the principal stress. Sigma 2, on the other hand, if you consider sigma 2 will represent minimum normal stress, right? So we have the formula for sigma 1 and we have the formula for sigma 2. Now, what is the formula for sigma 1? We'll use a plus sign. Like the formula for sigma 1 will be what? Sigma x plus sigma y by 2 plus square root of this whole thing, sigma x minus sigma y over 2 square plus tau xy square. So if you use a plus sign between these two, then it will be the formula for sigma 1, which denotes what? The maximum normal stress, right? And similarly, if you use a negative sign, then that will be the formula for sigma 2, and sigma 2 will denote what? Sigma x plus sigma y over 2 minus square root of this whole thing, and it will denote what? The minimum normal stress. And sigma 1 and sigma 2 are also called as the principal stresses, right? And the angle at which this stress happens, like you rotate the stress block, and at a certain angle you will obtain maximum normal stress and minimum normal stress. So that angle is called as theta p, where p stands for principal. So you can find out that angle P by using this formula. Tan 2 theta P is equal to what? 2 tau xy upon sigma x minus sigma y. Again, we have discussed all these things in detail in the class, and I'm just trying to recapitulate all these things, right? Again, for shear stress, maximum shear stress, you have to do is what you have to do is you have to differentiate this equation with respect to the angle theta, and then set it equal to 0, and then you'll find out the angle theta for which your shear stress will be maximum. That angle turns out to be what? Negative of sigma x minus sigma y divided by 2 times tau xy, right? So this equation will give you the maximum value of uh, the value of angle theta for which the shear stress will be maximum, right? So that is why it is called as theta s. And the maximum value of shear stress is what? Square root of sigma x minus sigma y over 2 square plus tau x y square. Now you can compare these two equations. The value of this tau max is nothing but this part, right? Okay. Again, one very important thing and one very interesting thing is this. If you add sigma 1 and sigma 2, right? Like sigma 1 is what? Sigma x plus sigma y over 2 plus square root of sigma x minus sigma y over 2 square plus tau x y square. And sigma 2 is what? Sigma x plus sigma y over 2 minus uh, square root of sigma x minus sigma y over 2 square plus tau x y square. So if you add sigma 1 and sigma 2, what you will find out is sigma 1 plus sigma 2 is will be equal to what? Sigma x plus sigma y. And I've already told you that the sum of the normal stresses is a stress invariant, right? So the sum of the normal stresses does not change with respect to the angle theta, even if the stresses are maximum and minimum stresses. Like so sigma 1 is what? The maximum normal stress. Sigma 2 is the minimum normal stress uh, based on the angle of rotation, and sigma 1 plus sigma 2 is coming out to be what? Sigma x plus sigma y, right? And also uh, you can use this equation if you were to subtract sigma 1 and sigma 2, like sigma 1 minus sigma 2, and you were to divide the result by 2, what you'll get is tau max. You can easily follow it from this mathematical equations, and we've already done all these things in the class, right? Okay. So I'll move on to the next topic, which is Mohr's circle. And Mohr circle is a very important part of study of strength of materials. Now, these equations which we have studied so far, like the equation for the normal stress in the rotated direction and for the shear stress in the rotated direction, these equations are called as analytical equations, right? So what you do is you plug in the values and you get the results, right? But suppose that you need to visualize that, right? You have to visualize the results without using the formula. So there is also one method for it, and that method is called as the Mohr circle, and it is a very interesting topic, and we'll see how to draw Mohr circle. But first we'll see what is a Mohr circle and how we can draw Mohr circle, right? So if you consider these two equations, sigma n and tau nt, sigma n or sigma x dash and tau nt or tau x dash y dash, uh, nothing but the same thing. So if you take this expression and you rearrange it, like you send the first term to the left hand side, then this equation will change to this one. This will become what? Sigma n minus sigma x plus sigma over 2, and this will be equal to what? Sigma x minus sigma over 2 cosine of 2 theta plus tau x point to sine of 2 theta. So what I have done is I have transported this first term to the left hand side. And I also have this second equation. What I'll do is I'll square this equation and I'll square this equation and I'll add the two equations. So if we square and add the two equations, what we'll get on the left hand side will be this square of this term sigma n minus sigma x plus sigma over 2 ka square plus tau nt ka square, and this will be equal to what? Square of this term plus square of this term, right? So if you do a little bit of algebra, you'll find out that the square of this equation reduces to this, and there will be uh, terms which contain cos square theta, and there will be terms which contain sine square theta, and your equation will come out like this. Okay. So this is the equation sigma x minus sigma over 2 cos square into cos square 2 theta plus sigma x minus sigma over 2 cos square into sin square 2 theta plus tau xy square sin square 2 theta plus tau xy square cos square 2 theta. What you can do is you can take out sigma x minus sigma over 2 square common from this equation. So what will remain is cos square 2 theta plus sin square 2 theta, which is equal to 1. And you can similarly take out tau xy square common from this side, and what will remain inside will be sin square 2 theta plus cos square 2 theta, which is again equal to 1 according to the trigonometric identities. So the final equation which you get by rearranging this thing is like this: sigma n minus sigma x plus sigma y over 2 square plus tau nt square is equal to what? Sigma x minus sigma y over 2 square plus tau xy square. So this is the final equation which we get after all the algebraic manipulation. Okay. Now, if you remember the equation of a circle, you might be remembering that the equation of a circle is given by such an equation where the equation is like this: x minus a whole square plus y minus b whole square is equal to r square, where A and B represent the center of the circle, right? So if this is a circle, you have A and B, and A and B represent what? The center of the circle. R is what? R is the radius of the circle, and X and Y are the X coordinate and Y coordinate, right? So this equation represents the equation of a circle. Now, if you compare this equation with this equation, first you have to rearrange it in this form. I'm just including a 0 over here, tau nt minus 0 square, just this small manipulation. And if you compare these two equations, you will find out that this equation represents the equation of a circle, right? With center. So here the center is what? A and B. And if you look in this equation, the center will be what? Sigma x plus sigma y over 2 and B, which is 0. So the center of this circle will be what? Sigma x plus sigma over 2 comma 0, and r square is this. So what will be r in this case? R will be equal to what? The square root of this thing, right? So uh, so the radius will be equal to what? The square root of sigma x minus sigma over 2 square plus tau xy square, and the center will be sigma x plus sigma over 2 comma 0. And also sigma x plus sigma y over 2 is nothing but we call it as the average normal stress, right? So this equation represents equation of a circle, and that circle is called as Mohr's circle, right? Um, that equation is called as Mohr circle. And also one thing you have to keep in mind is that this equation is obtained by squaring and adding these two equations, right? And the angle in these two equations was what? 2 theta, right? So Mohr circle is based on 2 theta angle, not theta angle. It is based on twice theta angle, right? One more thing I would like to mention over here is that if you compare these two equations, this is A, this 0 is B, and radius is the square root of this thing. And if you compare these two equations, sigma n is nothing but x, so it will be on the x-axis, and tau will be on the y-axis, right? So each point on this equation, on this circle, will represent a value of normal stress and shear stress, right? And again, you have to remember that this equation is based on twice theta, not theta. So Mohr circle is a circle where each point represents the stress sigma and tau on a particular plane through a single point, right? Okay. Now, if you have to draw Mohr circle, there are again certain sign conventions, and we'll use a different set of sign conventions as compared to the stress transformation equations. So we'll just discuss what are the sign conventions. They are partially different, not totally different. They are partially different, and we'll discuss what are the sign conventions, and we'll proceed further. Right? You have to remember this equation for the Mohr circle. Right? This is the radius, and this is the center. Now the sign conventions are like this. Sign conventions for the normal stresses are same as compared to the stress transformation equations. Like we consider tensile stresses to be positive, compressive stresses to be negative. The sign convention for shear stresses is a little bit different. In this case, we consider shear stress to be positive if it tries to rotate the element on which the shear stress is acting. It tries to rotate it clockwise, right? So if you consider this shear stress, then there will be a shear force on this plane, and what this shear stress is trying to do is this shear stress will try to rotate this plane in a clockwise direction, right? So in that case, you will consider it as positive. So if the shear stress tries to rotate the plane on which it is acting in a clockwise direction, then it is considered as positive clockwise stress. Else, if the shear stress is trying to rotate the face on which it is acting in an anti-clockwise direction, then you will consider it as a negative shear stress, right? So you can see that this shear stress will be negative shear stress. If you compare the sign convention with the previous sign conventions, all these shear stresses were positive, positive on positive, negative on negative, but we use a different set of sign conventions for the Mohr circle, and we are going to use these sign conventions, right? Okay. So let's just proceed further. So suppose that we have a stress block like this, right? And we have sigma x stress block. We have sigma x normal stress on this face, sigma y normal stress on this face, and similarly sigma x and sigma y over here, and tau xy on these faces. So first of all, what I would like to tell you is that we consider two faces, right? So first one is a face which I call as vertical face. So this is a vertical face. This face, this face is a vertical face, right? So this face is a vertical face, and again there is one horizontal face. So this is a horizontal face, right? So this is nothing but a horizontal face. So I've got two faces over here. I have got a vertical face and I have got a horizontal face. Uh, Now also you can see the sign conventions. Like according to our sign conventions, sigma x, if I consider this vertical face, so then in that case, for uh, for that vertical face, sigma x is what? Positive, because it is tensile, and the shear stress is what? Negative, because it is trying to rotate this face in an anti-clockwise direction. So that is why the value of shear stress is negative. Similarly, if you consider the horizontal face, which I have denoted by H, the value of normal stress is positive. So sigma y is, the sign for the normal stress is positive. So it will be plus sigma y, and shear stress is again positive. Why? Because the shear stress is trying to rotate this face in clockwise direction. So the coordinates for point H will be plus sigma y and plus tau xy, whereas for the vertical face, for this particular case, it will be plus sigma x and minus tau xy, right? And we have also seen that in this equation, sigma n plays the value of x and tau nt plays the value of y, right? And this is what? This is the center of the circle. So we'll consider two axes. This is like this one axis, horizontal x-axis, where this represents sigma, and then there is one vertical axis which represents tau or shear stress, right? Again, I would like to tell you that normal stress is positive on the right hand side of this point according to the normal sign conventions. Normal stress is negative on the left hand side. Shear stress is positive uh, on the upside of this point, and similarly it is negative downside, right? So what we'll try to do is we will try to plot one circle, and I'll prove that that circle is equal to Mohr circle, or that circle represents Mohr circle, right? So I have got the coordinates of these two faces. Like I've got the coordinate for a horizontal face and for a vertical face, right? And for the time being, I'm considering that the value of sigma x is greater than sigma y, right? So what I can do is I can plot these two points, this horizontal point and this vertical point onto this diagram, right? So if I were to plot the vertical face, so vertical face is what? Plus sigma x and minus tau xy. So I'll have to move in this direction for plus sigma x. So suppose this point represents the value of sigma x, and I'll have to move in downward direction because it is minus tau xy, right? So this point will represent what? This point will represent v, where the coordinates of this point v are what? Plus sigma x and minus tau xy. Similarly, for plotting this point h, it is what? Plus sigma y and plus tau xy. So again, it is on the right hand side, but it is on the upside of this. So if I consider this point will represent point h, right? And what I'll do is I'll join these two points using a line. So So I have joined the 2 points, the vertical point and the horizontal point using a straight line. And considering that straight line as a diameter, I'll draw a circle around that line, right? So I have drawn a circle like this, considering that line as my diameter. Now my claim is that this circle is, the circle represents Mohr circle, right? But we'll have to prove that. How does this circle represents Mohr circle? So we'll do that. We'll have to prove that this circle represents Mohr circle. And again, I would like to tell you that the coordinates of this point is sigma x minus tau xy, and this point is sigma x tau xy, sigma y tau xy, right? Okay. So this is the condition. This is my vertical point, and this is my horizontal point, right? And I've got the coordinates of these 2 points. Okay. Uh, so this is the circle. Uh, now consider this. This is my origin, right? uh, and if I take the distance of this point to this point along this axis, like this distance, so this distance is what? Sigma y, right? So this distance is nothing but sigma y. Similarly, if I take the distance of point v from this axis along the horizontal axis, then that distance will be what? Sigma x. So this distance is sigma y, this distance is sigma x, and so the distance between these 2 points, or the distance between point H and point V measured along the horizontal axis, like this distance, will be equal to what? Sigma x minus sigma y. So this distance is nothing but sigma x minus sigma y. And if I consider this as a center, then this distance will be what? Sigma x minus sigma y over 2, and this distance will be sigma x minus sigma y over 2, right? Okay. So suppose that you consider length OC, you have to find out length OC. Then how can you find out length OC? You'll have to add this distance from here to here plus this distance here to here. Okay. So you know this distance is nothing but sigma y, and this distance is nothing but sigma x minus sigma y over 2. So length OC can be found out as sigma y plus sigma x minus sigma y over 2. And when you solve this, you'll find out that length OC is equal to what? Sigma x plus sigma y over 2, right? So this length OC is nothing but sigma x plus sigma y over 2. And if I consider the coordinates of this point C, you'll find out that the x coordinate, right? The x coordinate for this is what? Sigma x plus sigma y over 2, and the y coordinate is what? 0, because it is on this horizontal line. So the coordinates of point C is what? Sigma x plus sigma y over 2, comma 0. And if you remember, the coordinates for the center of a Mohr circle, the coordinates for the center of a Mohr circle were what? Sigma x plus sigma over 2, comma 0. So the coordinates of the center for this circle, the coordinates of the center for this circle which we have drawn, are same as the coordinates of the center of a Mohr circle, right? So the center for both the circles are same. Okay. Next, what we'll do is we'll consider the radius of the circle, because if how do you define a circle? You need if you have to define a circle, then you need a radius and a center. Once you define what the center of the circle is, once you define what the radius of the circle is, then you end up defining properly what a circle is, right? Because these two things, these two properties define a circle. If you change any one of the properties, then the circle will change. Okay, so uh, we have defined what the center is. We have found out what the center of the circle is, and it is equal to the center of the Mohr circle. Next, we'll find out what the radius of the circle is, right? So if I consider this height is nothing but tau xy, and this distance is what? Sigma x minus sigma y over 2, right? And this represents this ch. This represents what? The radius of this circle, right? So I can find out the radius of the circle. Radius of the circle will be find out by what? Using the Pythagoras theorem. And you can see that the radius of the circle is given by square root of sigma x minus sigma y over 2 square plus tau xy square. So the radius of this circle is nothing but this. And if you remember the radius of Mohr circle, it was also given by this. So the radius of Mohr circle is also given by this square root of sigma x minus sigma y over 2 square plus tau xy square, right? Uh, so the radius of this circle is also equal to the radius of Mohr circle. So now the two properties which are required for defining the circle, which is what? The center and the radius, both the properties for the circle which we have drawn are equal to the properties for the Mohr circle. Like the center of the circle is equal to the center of the Mohr circle, and the radius of the circle is equal to the radius of the Mohr circle. So this circle indeed represents what? A Mohr's circle, because its center is same and the radius is same. So this circle is nothing but a Mohr's circle, right? So this circle represents a Mohr circle. Now we can plot a few additional points onto this circle. First point is uh, we can plot maximum normal stress and minimum normal stress, right? So if you consider this circle, each and every point on the circle will represent the state of stress at a particular point at a particular orientation, right? And if you consider this point, if you consider this point, so this point will represent what? At this point, the value of normal stress is what? Normal stress is maximum, and the value of shear stress is 0. So this represents what? This represents your principal stress or the maximum normal stress, right? So sigma 1 stands for your principal stress. Sigma 1 stands for your principal stress, and this point represents what? Your maximum normal stress. Similarly, this point, uh, at this point, the value of normal stress is minimum, and thus this point will represent minimum normal stress, right? And again, this sigma 1 and sigma 2 are nothing but the principal stresses. Principal stresses, because the normal stresses are maximum. And you can again see one thing, that when the normal stresses are maximum, the shear stress on this point and the shear stress on this point is 0, right? So this is one of the properties, like when the normal stress is maximum, the shear stress is 0. But the opposite of this is not true, right? So if you find out the value of maximum shear stress, so we'll have to move in vertically upward direction. So through the center, and it will be the highest point. So this point will represent what? Tau max, right? And one thing you can see is that the value when shear stress is maximum, your normal stress is not necessarily 0, right? It is not necessarily 0. But when your normal stress is maximum, the value of shear stress is necessarily 0, right? Also, we always consider this face, like the vertical face, as our reference point, right? We have discussed this many times in a class, that we consider this face, this vertical face, as our reference face. So this point V will be our reference point, and will mark all the angles using this line CV as our reference, right? So if you remember the angle at which the maximum normal stress occurs, we call it as theta p. And since Mohr circle is based on twice the angle, so this angle will represent what? 2 theta p. Like you have to move from this face to this face. So this angle will represent 2 theta p. At this angle, the normal stress is maximum. And similarly, this angle will be what? 2 times theta s. So at this angle, the shear stress is maximum. So on Mohr circle, you use twice the angle as that on the stress block, right? So I think this has become clear that why does this circle represents a Mohr circle, and it will again become clear when we solve examples. Uh, Again, one thing which has remained over here is this. Suppose that you have to find out the value of the stress on this plane AA, right? So this plane AA is can be obtained by rotating this vertical face anti-clockwise, right, in an anti-clockwise direction, uh, and by which angle? So this angle is what? Since this angle is theta A, so again uh, this angle, like, so if this angle is theta A, then this angle will also be theta A. And if I rotate this vertical, if I rotate this vertical in anti-clockwise by an angle of theta A, then I'll get this plane AA, right? So in order to get the plane AA, I'll have to rotate the vertical face anti-clockwise by an angle of theta A. So again anti-clockwise, and we will consider this as a reference. So I'll have to move by twice of theta A in order to reach this stresses on that point, right? Because if I rotate this stress block by an angle theta, then I'll have to move by angle 2 theta on Mohr circle, right? So I move by this angle twice of theta A from this point, taking this as reference, CV as reference. So I'll move by an angle twice of theta A, right? So I'll reach point A, and then I can directly read what is the value of the normal stress and what is the value of shear stress on that plane AA, right? So for example, the value of normal stress on that plane A is sigma A, and the value of shear stress on that plane is tau A, right? So this is again the same thing. I would again like to summarize what we have seen till this point. We had this stress block. We have the various stresses shown on this stress block. There is one stress sigma x, which is normal tensile and it's positive. Tau xy, and this is negative because this shear stress is trying to rotate this face in an anti-clockwise direction. Sigma y is again positive tensile. Tau yx in this case is positive because it is trying to rotate this face in clockwise direction. So we have got these 2 points V and H, where V is for this vertical face and H is for this horizontal face, right? So the coordinates of point V will be plus sigma x and minus tau xy, and the coordinates of this point H is plus sigma y and plus tau xy. What we do is we plot the points H and V onto this coordinates of sigma and tau, and we join the 2 points V and H, and consider join the 2 points by a line, and by considering that line as a diameter, we make a circle, right? So this is a circle, and this circle represents what? The Mohr circle, because the center of the circle is equal to the center of the Mohr circle, and the radius of the circle is equal to the radius of the Mohr circle, right? And again, this point represents sigma 1 maximum normal stress. This point represents sigma 2 minimum normal stress. This point represents tau max maximum shear stress. This angle is 2 theta p, because you have to move twice the angle. If you rotate your stress block by some angle theta, then you'll have to rotate, you'll have to move by an angle twice theta onto the Mohr circle, right? Again, if you have to find out what is the normal stress and the shear stress on this plane AA, then what you have to do is you have to rotate this vertical face in an anti-clockwise direction by angle theta A. So in this case, you have to rotate it by an angle of theta A. On Mohr circle, you'll do is you will move by an angle of twice theta A. And again, considering this as your reference, CV as your reference, so you will move by an angle of twice theta A. So you'll reach at this point, and at this point you can find out what is the value of the normal stress and what is the value of the shear stress. And for example, it is sigma na tau A, right? And 2 theta p is what? The angle at which the normal stress is maximum, and theta is what? Twice theta is what? The angle at which the value of shear stress is maximum, right? So we'll solve an example. So suppose that this stress block, so the question is like this: the stress block shown represents stresses on two orthogonal planes through a point in a structural member. Using Mohr circles, find number one, the principal stress and maximum shear stress at that point, and show the planes on which they act on a properly oriented stress block. And number two is the normal stress and the shear stress on a plane A through a point on a properly oriented stress block, right? So we have to find out, so this is our given condition, and we have to find out for this given condition what is maximum normal stress and what is the maximum shear stress, and we also have to represent it. We also have to draw a rotated stress block, right? So we'll do the first part, but again, first we have to decide what is the value of sigma x and sigma y. So sigma x is what? 140 megapascal, but when we take it, we'll take it as minus 140 megapascal, right? Because it's compressive, right? And sigma y is what? Plus 100 megapascal tensile. Similarly, this shear stress, now this shear stress will be what? Positive. For our case, it is shown as negative overhead. Tau xy is what? Minus 50 megapascal. So shear stress will be negative. Shear stress will be positive because this shear stress is trying to rotate this face in a clockwise direction, and this shear stress will be what? Negative, right? So I have the coordinates. I have the coordinates of point H and point V. Right. So we have got the coordinates of these 2 points, horizontal face and vertical face, and we have plotted these 2 points, horizontal and vertical, over here. Right. Again, I want you to consider this. For vertical face, normal stress is negative, right? For the vertical face, your normal stress is minus 140, and though shear stress is given as negative over here, we will consider the shear stress as positive, right? So minus 140 comma 50 positive, and similarly for the horizontal case it is 100 comma minus 50, right? So we'll join these 2 points, and we'll consider that line as a circle, and we'll consider that line as a diameter, and we'll draw a circle. So we have drawn a circle over here. Okay, this is the center. Now we know what the center is, right? So center is what? Sigma x plus sigma y over 2. So it will be sigma x is nothing but minus 140 plus sigma y is nothing but 100 over 2 comma 0. So your center turns out to be minus 20 comma 0. So this is your center. Again, the point of intersection of this line with the horizontal axis is will be nothing but your center, right? Okay. And also you can find out the radius using this formula, square root of sigma x minus sigma y over 2 square plus tau x by tau square, right? So your radius turns out to be 130. Okay. Also, The maximum value of shear stress is nothing but your radius. So your tau max will be what? Plus 130 megapascal, right? Okay. Uh, Next, what you have to do is you have to find out the value of sigma 1 and sigma 2, right? You have to find out what is sigma 1 and sigma 2. So you can very easily find out the value of sigma 1 and sigma. So the value of you can very easily find out the value of sigma 1 and sigma 2. So this is the center. Now what is this distance? This distance is nothing but minus 20, right? Because the coordinates of this point is minus 20, 0. This is the origin. So this distance is nothing but minus 20. And what about this distance? This distance will represent the radius of the circle, right? And we know what the radius of the circle is. Radius of the circle is 130. So we can find out the value of sigma 1. So sigma 1 will be what? Minus 20 plus 130. So sigma 1 will be equal to minus 20 plus 130. It will turn out to be 110 megapascal, and it is positive tensile, right? So the value of sigma 1, which represents maximum normal stress, is 110 megapascal. Similarly, you can find out the value of uh, sigma 2, right? So sigma 2 will represent what? Sigma 2 will represent uh, sigma 2 will represent the value of minimum normal stress, right? Uh, I'd just like to go back to the calculation of sigma 1, right? Uh, this is the center of my circle. So this distance, right, from this point to this point, to this point, this is the total radius, right? And if I have to find out the value of sigma 1, then we always calculate the value from the origin, right? So we'll have to find out this distance, right? So how can we find out this distance? We'll have to take the value of the radius from this point to this point, from center to this point, and we'll have to subtract this distance, right? So that we get the distance from the origin, right? So sigma 1 will be equal to what? This distance is what? 130, and this distance is what? 20. So sigma 1 will be equal to 130 minus 20, which is equal to 110 megapascal. So we always measure distances from the origin, right? So sigma 1 is nothing but 110 megapascal. Now, if I have to find out the value of sigma 2, then this is the center, this is the radius. So this distance is nothing but 130, right? And this distance is what? 20 minus 20 minus 130. So if I have to calculate the distance of this point from the origin, so sigma 2 will be equal to what? Minus 20 plus minus 130, right? So minus 20 minus 130 is nothing but minus 160. So the value of sigma 2 is what? Minus 160 megapascal, and it is compressive, right? So we have find out the value of sigma 1 and sigma 2. We've also find out the maximum value of shear stress, right? And also we can find out the value of 2 theta p, right? Because what we know is what we know this, right? We know the value of shear stress at this point, which is nothing but minus 50, right? We know what the radius is, so we can very easily find out this angle 2 theta p by using this trigonometric identity. Sine of 2 theta p is equal to what? 50 upon 130, and 2 theta p will be equal to what? 22.6. So this angle 2 theta p is nothing but 22.6 degrees. Also, please note that we move twice on the Mohr circle. Uh, if we move by an angle theta on the stress block, then we move by angle 2 theta on the Mohr circle, right? So if this angle is 22.6 degrees, 2 twice of theta p is 22.6 degrees, then theta p will be equal to what? Half of this, which is 11.3 degrees, right? And this is what, if you now consider this is the center, and this point is nothing but the horizontal point, right? So this represents your horizontal face, right? And you have to rotate the horizontal face by angle theta p, by angle 2 theta p on Mohr circle, and in real by angle theta p. So this is the horizontal face, and you'll have to rotate it by an angle of theta p, which is 11.3 degree horizontal face, right? So this point is horizontal, so you have to rotate it by angle 11.3 degrees, and again in an anti-clockwise direction, right? So in an anti-clockwise direction. So this plane will represent what? This plane will represent a point where your normal stress is what? Sigma 1, which is 110 megapascal. So this normal stress on this plane will be 110 megapascal. Similarly, the normal stress on this plane will be 110 megapascal, and on the remaining two faces it will be minus 160 and minus 160, right? Sorry, minus 150 and minus 150 megapascal, right? And again, the shear stress on this this state of stress will be what? Zero, because the shear stress at this point is zero and the shear stress at this point is zero, right? So if you take this stress block and you rotate it by an angle of 11.3 degrees in an anti-clockwise direction, then this is your new state of stress, and this state of stress is what? Principal stresses. The stresses on this block are principal stresses, right? Okay, so we are done with the first part, right? Now I'll move on to find out the value of the stresses on this plane AA, right? So we also have to find out the value of this stresses on this plane AA. So how can we do that? First, we'll have to find out the angle theta A. For that, we have been given that this rise upon run. So the run is 4 and the rise is 3. So we can very easily find out this angle theta A by using tan inverse 3 by 4, and it turns out to be 36.9 degrees. So this angle theta A, now I'm measuring the angle theta A from the horizontal face. Please note this, that I'm measuring this angle theta A from the horizontal face. So if I have to get to this face AA, then I'll have to rotate the horizontal face by an angle of theta A on the stress block, right? And on the Mohr circle, I'll have to rotate it by an angle of twice of theta A, right? So this is my Mohr circle, this is my horizontal point, this is my vertical point. So I'll consider this as a reference now, because I'm rotating my horizontal face by an angle of uh, theta A, right, on this stress block and in an anti-clockwise direction, right? So what I'll do is I'll rotate this CH in an anti-clockwise direction by an angle of twice theta A, right? So twice theta A turns out to be 73.7 on the Mohr circle, right? So I'll rotate this by twice of theta A. So this is twice of theta A, and this point represents what? This point represents the stresses on point A, right? So I can drop a perpendicular and I can read my sigma from this point, and I can read my tau from this point, or we can also do it like this, right? So I know what the radius of my circle is. So this CA represents what? The radius of my circle. I know what twice theta A is. I know what twice theta P is. We have calculated it in the previous slides. So I can calculate this angle phi. Phi will be equal to what? Twice of theta A minus twice of theta P. Twice theta A is 73.7 degrees. Twice theta P is 22.6 degrees. So I'll get angle phi as 51.1 degrees, right? So this angle is nothing but 51.1 degrees, which I'm calling as phi. I also know CA, which is the radius. So if I want to find out this distance, right, this distance, so what I can do is radius, I can project this radius onto the horizontal axis. So for that, I'll have to use sine of phi. So sine of phi will be equal to what? Tau A upon r radius. So I can find out tau A for this, which will turn out to be 101 megapascal. And similarly, I can find out the value of sigma A, right? So how can I find out the value of sigma A, the normal stress at this point? So the value of sigma A will be equal to what? Measured from the origin to this. So this length will represent what? This length will represent the normal stress on point A. So how can I find out this normal? So what we can do is we can project this. So we'll do this length minus this length, right? So what is this length from this point to this point? It is nothing but r into uh, r into cos of this phi. So r is what? 130 into cos of 51.1. So it will represent this length, and I'll subtract this length, which is nothing but 20. So I'll get 130 into cos of 51.1 minus 20, which is 61.6. So I have sigma A as 61.6 megapascal, and it is again tensile. So I have very easily found out what are the stresses, normal stresses and shear stress on point A, right? And one thing you can do is you can plot the stresses in the rotated condition, right? So how did you find out AA? You took your horizontal face and you rotated it in an anti-clockwise direction by theta A, right? So theta A was 36.6. So I'll take my horizontal face and I'll rotate it by 36.9 degrees, right? And we've already calculated what is the normal stress and what is the shear stress. Normal stress was 61.6 megapascal tensile, and the shear stress was 101 megapascal. And please note that the shear stress was positive, right? And what does positive in this case means? Positive means the shear stress will rotate it in clockwise direction. The face on which the shear stress is rotating, the shear stress is acting, it will try to rotate that face in clockwise direction, right? So this shear stress will try to rotate this face in a clockwise direction. So this is the direction of the shear stress, right? So I hope that the concept of Mohr circle was clear to you. If you have any problem, you can raise it on a discussion forum on our website. Again, all the PPTs and all the lecture notes are available on our website. The link of this video will also be available on our website. And if you have any query, you can contact me personally, right? Uh, Thank you and stay safe.